Stoichiometry Part 2. In the first part of our stoichiometry section, we assumed that there was always enough of each of the chemicals for the reaction to go to completion, and that everything would be used up during the reaction. But that's not always the case. Let's look at this particular example. Let's say that we have magnesium reacting with iodine to produce magnesium iodide. It's a synthesis reaction because we have two elements forming one compound. It's also a balanced equation because we have one magnesium, two iodines, two iodines. So we want to identify which is the limiting reagent or the limiting reactant in this particular reaction given different quantities. The limiting reactant or the limiting reagent is the substance that we run out of in a chemical reaction. The other substance would be referred to as the excess. And our balanced equation tells us how substances react. So let's say that we start out with 100 atoms of magnesium and 100 diatomic molecules of iodine. Well, the balanced equation is a 1-to-1 ratio. And that ratio is an atom ratio or a particle ratio or a mole ratio. So 100 atoms to 100 diatomic molecules, that's a 1-to-1 ratio. So everything would be consumed in this reaction and we would have no excess. Well, let's say that we start out with 150 atoms of magnesium and 100 diatomic molecules of iodine. Well, 150 to 100 is not a 1-to-1 ratio this time. The iodine is going to completely react. All 100 diatomic molecules of iodine will react with 100 atoms of magnesium. So iodine's our limiting reactant. Magnesium would be considered the excess. And if 100 atoms reacted before all the iodine ran out, we'd have 100 or we'd have 50 atoms of magnesium left over. So let's say that we start out with 200 atoms of magnesium and 300 diatomic molecules of iodine. 200 to 300 is not the 1-to-1 ratio the balanced equation tells us. In this case, 200 atoms of magnesium will react with 200 diatomic molecules of iodine, leaving us with 100 diatomic molecules of iodine unreacted. So magnesium would be our limiting reactant or our limiting reagent, and iodine would be in excess. Well, now let's look at moles. Our balanced equation is also a mole ratio. So if we have 0.16 moles of magnesium reacting with 0.25 moles of iodine, and the balanced equation tells us it's a 1-to-1 ratio, all 0.16 moles of magnesium will react with 0.16 moles of iodine, leaving us with an excess of 0.09 moles of iodine. So magnesium's our limiting reagent and iodine is our excess. 0.14 moles of magnesium and 0.14 moles of iodine, well, that's a 1-to-1 ratio, which follows the balanced equation. So everything is consumed. There is no limiting reactant and excess reactant. 0.12 moles of magnesium and 0.08 moles of iodine is not in a 1-to-1 ratio. Iodine would be the limiting reagent. 0.08 moles of iodine would react with 0.08 moles of magnesium, and we'd have an excess of 0.04 moles of magnesium. Now, this is a trick. 1.00 grams of magnesium and 2.00 grams of iodine, well, a balanced equation is not a gram ratio. It's a mole ratio. So we can't just take the grams of the substances and figure out what our limiting and our excess reactants are. We would have to convert grams to moles first and then determine which is our limiting reactant. So here's an example. Let's say that we have 17.82 grams of sodium hydroxide and we're going to react it with 15.40 grams of phosphoric acid. And we're given sodium phosphate and water as our products. We don't necessarily need to be given that because it's a double displacement reaction and we can predict it, but the question gave us some extra information. We want to decide which reactant is the limiting reactant, and then we want to find out how much sodium phosphate can be formed. So let's work our problem out. Our first step is going to be to balance our equation. So sodium hydroxide plus 1 minus 1 plus phosphoric acid. Remember that acids have hydrogen as their positive ion. Phosphates are negative ion, plus 1 minus 3. And we're going to produce sodium phosphate plus 1 minus 3 and water, which I'm going to write as HOH. It makes it a little easier to balance. You can write it as H2O. So we have 1 sodium, 3 sodiums. That'll balance out the sodiums. 3 hydroxides, 1 hydroxide. That'll balance out our hydroxides. 3 hydrogens, 3 hydrogens, 1 phosphate, 1 phosphate. So we have a balanced equation. Going back to the question, we have 17.82 grams of sodium hydroxide and 15.40 grams of phosphoric acid. We eventually want to find out how many grams of sodium phosphate are produced. Well, whenever we're given the amount of both reactants, we're looking at a limiting reactant problem. So we need to decide which is our limiting reactant, and that will limit how much product we can produce. We can't compare things in terms of grams, so we're going to have to do a conversion from grams to moles first. 17.82 grams of sodium hydroxide. We're going to go from grams of sodium hydroxide to moles of sodium hydroxide. We know that 1 mole equals our molar mass. And for sodium hydroxide, that's 40.00 grams. We want 4 significant digits, so 0.4455 moles of sodium hydroxide is what we're starting with. We're going to take 15.40 grams of phosphoric acid and convert that to moles. So we're going to cancel out grams and go to moles. 1 mole equals our molar mass, and for phosphoric acid, that's 98.00 grams. So we have 0.1571 moles of phosphoric acid to start with. Now we can't just look at those two numbers and decide which is our limiting reactant, because the balanced equation tells us that 3 moles of sodium hydroxide react for every 1 mole of phosphoric acid. So we're going to divide sodium hydroxide by 3 and divide phosphoric acid by 1. We're going to get 0.1485 and 0.1571. The smaller number is what's going to tell us what our limiting reactant is. So that means that sodium hydroxide is the limiting reactant. There's step 1. Now we're going to use the amount of limiting reactant to determine how much product we can produce. So we'll take 0.4455 moles of sodium hydroxide. Our balanced equation tells us that for every 3 moles of sodium hydroxide that reacts, we're going to produce 1 mole of sodium phosphate. And then we'll go back to grams. 1 mole of sodium phosphate is the molar mass, which is 163.94 grams. So we can produce 24.35 grams of sodium phosphate before the sodium hydroxide runs out. And once the sodium hydroxide runs out, we can no longer produce product. Theoretical yield. The theoretical yield is what the stoichiometry tells us we can produce. It's the maximum amount of a given product that can be formed when a limiting reactant is completely consumed. The percent yield is a relationship between how much we actually produced in lab and how much we can theoretically produce on paper. So to figure out the percent yield, we would take the actual yield, or the experimental yield, divide it by the theoretical yield, or the stoichiometry value, multiply it by 100, and that would give us our percent yield.